All right, let's talk about root locus. Root locus is invented around 1940s by Walter Evans. So it is nothing but a graphical method to analyze stability and transient performance of a closed-loop system as a function of gain k. Something, for example, like this. You have in this unity feedback system, you have some forward loop transfer function. Here, G can be composed of controller transfer function multiplied by the plant transfer function. I am just going to denote it as G. So if you write the closed loop system transfer function between Y and R, you have this form. And here, closed loop poles can be found by setting its denominator to 0 and solving it for S. Before even we start talking about root locus, consider a simple open loop system like this. Insert this to this closed loop form. If you do so, you have the closed loop system transfer function appearing like this. And to determine the stability of the closed loop system, we just take its denominator, set it to 0, like in here, and solve for S. In this case, we have this S equals to minus 1 minus K. So let's look at this table. If you give K equals to 0, closed loop pole is located at 1, which is an unstable system. If you give gain K 1, you are going to have 0, like in here, marginally stable closed loop system. And for any value of gain K greater than 1, for example, if you give 2, 1 minus 2 is minus 1, 1 minus 3 is minus 2. So if you plot this on the complex plane, real axis and imaginary axis, when gain K equals to 0, you are at the open loop unstable pole or forward loop. When gain is 1, you converge to this point. When gain is 2, you converge to this point. And when gain is 3, you converge to this point. So if you look at this trend, you can say that as you increase your gain from 0 to infinity, you follow a pattern, you follow this line in this simple case of this transfer function. Well, when we sketch root locus, we are not going to do like this, okay? So instead of finding the closed loop system transfer function and setting its denominator to 0 and solve for S, for different values of gain K, we will use forward loop transfer function. Here is your forward loop transfer function, or here it is. And by only using this forward loop transfer function, we are going to sketch. All right, let's start. Now let's look at this forward loop transfer function here. Basically, it has a numerator and a denominator. When you set its numerator to 0, you are going to get, say, m forward loop zeros. When you set its denominator to 0, you are going to get, say, n forward loop poles. Based on this, we are going to establish some root locus sketching laws. And the first one goes like this. You have n forward loop poles, and so root locus will have n branches. These branches will be symmetric about the real axis. Real axis, real axis, real axis. And these branches cannot cross. Second rule, on the real axis, root locus exists to the left of an odd number of real axis poles and zeros. Let's consider these 6 examples. What this rule means, starting always from this side, root locus exists between here, two real axis poles in this case. Let's move into the second example. Starting from here, root locus exists from here to here, skipping the second gap, and from here to infinity. Moving to the third example, starting from here, root locus exists between here and here, skipping the second one and the third one. We don't care any non-real axis poles or zeros. Fourth example, starting from here, well, we don't have anything on the real axis, so root locus does not exist on the real axis. In these examples, we only sketch the root locus on real axis. Of course, root locus may or may not exist beyond the real axis, but this rule just focuses on the real axis. Fifth example, starting from here, root locus exists between here and there, skipping the second gap, root locus exists here, there is no other gap. And finally, root locus exists from here, skip here, here, and mark here. So these are the, red locations are the ones where the root locus exists on the real axis. Moving to another rule. To understand this rule, let's remember the closed-loop system for unity feedback configuration. And once again say that this G has this numerator, this denominator. Plug this G inside here, you are going to arrive this equation. Well, we now have some observations. First of all, take this denominator and set it to 0, which is here. When gain k is 0, this term disappears, so you end up having this. Now, let's take this equation, multiply from left and right by k inverse. You are going to arrive this equation. When gain is infinity, this term will disappear, so you end up having this. In other words, what I am trying to say is, when gain k is 0, root locus closed poles match with the forward loop transfer functions denominator or forward loop transfer functions poles. When gain equals to infinity, closed loop poles do match with the poles of with the zeros of the forward loop transfer function. This means the following. When the number of forward loop poles equals to forward loop zeros, these branches start at forward loop poles and end at the forward loop zeros. Consider a simple case. You have one forward loop zero, one forward loop pole. Basically, starting from here, root locus exists between these two. Basically, we say that k equals to 0, you are here, k equals to infinity, you are there. Moving from forward loop pole to forward loop 0. So let's put an arrow. So this means that your closed loop system, your closed loop pole, n equals to 1, so you are going to have only one closed loop pole. As you increase your gain k, your closed loop system becomes more unstable in this case, since you are on the right half plane. You go from 0 to 1. All right, what if you don't have n equals to m? So if n is greater than m, first of all, m branches will go to forward loop zeros. The remaining n minus m branches will approach to asymptotes originated at sigma of a with angles theta of A. I will immediately do an example, but first let's define sigma of A and theta of A. Sigma of A are the intersection point of these asymptotes. How you find this intersection point is summation from 1 to n, real part of the poles, minus I to m, real part of zeros, divided by n minus m. And you need also an angle for these asymptotes. This will be super clear in the next example. We use this equation, 2i plus 1, 180 divided by n minus m, and you are going to give to I 0 plus 1 plus minus 1 plus minus 2, so on and so forth. You are looking for n minus m unique or different angle values. Let's do an example. Let's consider this closed loop system. Here is your forward loop transfer function. You have no zero, so m is 0. You have 3 poles, so n is 3, meaning that you are going to have 3 branches. M branches will go to zeros. You don't have zeros. So remaining n minus m, 3 branches will follow asymptotes. So let's find the asymptotes. Using this formula, right, you have poles originated at 0, minus 1 and minus 5. Here, minus you have no zeros, divided by n minus m, 3. These asymptotes are originated at minus 2. Now angles. You are looking for only 3 different angles because n minus m is 3. You are looking for n minus m different values. So if you select I equals to 0, 1 and 2, you are going to get from this expression 60 degrees, 180 degrees and 300 degrees. So these asymptotes are basically originated at minus 2. Here it is. One of them is 60 degrees like this. The other one is 180 degrees. And the last one is 300 degrees. So if you sketch, starting from here, root locus exists between here and there, and skipping the second gap, and here and there. So now, this one is already on the asymptote. So basically, it goes like this. It is k equals to 0, you are here. K equals to infinity, it is on the asymptote. Now, remembering the first rule, the remaining 2 branches needs to approach these asymptotes. But it has to be in a symmetric fashion. It cannot go like this or like this. So as you increase gain k equals to 0, you are at the pole, you are at the forward loop pole. They must approach to each other, and at some point, so-called breakout point, one goes up, one goes down in a symmetric fashion with respect to real axis. And that's the only shape you can get with respect to the root locus. Now, of course, there are some important points, right? Like this and this and this important. So we need to discuss 2 additional rules to locate these points, especially this one, right? So basically, if you increase your gain k further than whatever this value is for that, let's call it k star, your closed loop system will be unstable. So to maintain the closed loop stability, your gain k must be less than k star. This brings us to this additional rule. To determine for what value of k root locus crosses imaginary axis, substitute s equals to j omega, y, real axis, imaginary axis, this is s equals to sigma plus j omega. And when you are at the imaginary axis, you only have j omega, you don't have the real part, or real part having 0. So find the closed loop system's denominator, substitute s equals to j omega, and solve for k and omega to find the value of gain k that it crosses the imaginary axis and the omega where it crosses. Let's turn back to our example. Now, this was the plot that we made. Now, for this system, if you write the closed loop system, you have this closed loop system transfer function. This is the denominator. Take this denominator, set it to 0, and instead of s, insert j omega. Then you have this point. This is an imaginary number, right? You have 0 equals to a plus jb, with this being a, this being b. For an imaginary number to be 0, a needs to be 0 and b needs to be 0. So this gives us two equations. From the first equation, set it to 0, you have this. Omega equals to 0, this point. This is not the point that we look for. We are looking for non-zero points. So here, if you select omega to the power of 2 to 5, you are going to get plus and minus square root of 5, this point and this point. And now, if you take this omega value, insert to this second equation, k, like this, you are going to get gain k equals to 30. In other words, to maintain closed loop stability, gain k must be less than 30. Why? Because if you increase gain, here is gain k equals to 30 and gain k equals to 0 and 0. If you increase gain k more than 30, your closed loop system will be unstable. All right, so I mentioned breakout point. So in fact, you may have break in and out points. To illustrate this and introduce to the final important root locus sketching rule, let's consider the unity feedback system with this forward loop transfer function. N equals to 2, M equals to 2, right? You have two zeros located at -2, -4, they are here. You have two poles located at 2 and 4, they are here. On real axis, root locus exists between here to here and there, skipping the second gap and here. Now, root locus must be symmetric with respect to the real axis, rule number 1. So the only way that they go from here to there, it needs to be this shape. Acknowledging the fact that at poles k equals to 0, k equals to infinity, we put arrows like this. Now, important thing is, first of all, let's use this gain equation. This was closed loop system's denominator. Equivalently, we can write it like this. Remember that in general, S is sigma plus j omega. Let's focus on the real axis when S is sigma. So take this gain equation, insert S equals to sigma, you end up having this. Within the context of this example, this. Right? 1 divided by this. Now let's focus on here. You increase k from 0 to some value. Likewise here. This value, let's say k1, is the maximum value of gain k on this local real axis interval. So this is the maximum of this interval. Likewise, this gain k, let's say k2, is the minimum because as you increase it further, you converge to k equals to infinity and k equals to infinity. So on this local real axis interval, k2 is the minimum. Now, if you have a gain function like this, how do you find minimum and a maximum? Well, you take its partial derivative with respect to real axis, set it to 0. This is exactly what we're gonna do for this example. Take this gain k, take its derivative, set it to 0, or equivalently this. For this to be 0, its numerator needs to be 0, or sigma 2 to the power of 8 needs to be 0. From here we get sigma plus minus square root of 8. So in other words, basically this point is exactly square root of 8 and this point is exactly minus square root of 8. But we would like to get a value of gain k when we are at this point. If you go back and insert these numbers to the gain equation coming from here, you are going to get 0.029, meaning that for k equals to 0.029, you are at this point. If you insert minus square root of 8, for gain equals to 33.97, you are at this point. For example, if you would like to have a closed-loop system which is stable and transient-wise, that does not oscillate, then you should choose your gain k larger than this 33.97, such that one closed-loop pole lives here and the other one is here. And since they don't have any imaginary axis component, your closed-loop system will not oscillate, right? If you choose your gain k slightly less than 33, let's say 25, one closed-loop pole is here, other one is here, your system will be underdamped because of these imaginary values, and your system will oscillate. This is coming from the solution of the system. This may be a topic for a different video. But if you choose your gain k exactly at 33.97, your closed-loop system will be critically damped. If you choose your gain more than 33.97, one pole will live here, other one will be here, your system will be overdamped. So this is the transients that we understand from the root locus. If you choose your gain k, accordingly, you can have a closed-loop system, not only stable, but also no oscillations. All right, so now as we learn the rules, let's roughly sketch the root locus for a couple of candidates. For example, here we start from here, sketch the root locus. N is 2, M is 0. So there will be a intersection point for the asymptotes. Asymptotes will have 90 degrees and minus 90 degrees. In this case, root locus will look like this. Starting from here, k goes to infinity, k goes to infinity, k is 0, k is 0. Now, in this case, instead of having this line here, root locus will be a point. Again, the intersection point, for example, give a number -1, write sigma of A is -1 divided by n minus m2 -1. Angles 2i plus 1 divided by n minus m2 multiplied 180, or 90 degrees. If you give I equals to 0, you get 90 degrees, I equals to 1 minus 90 degrees. So you will follow asymptotes like this. Now, this third one is similar to this one in other, this example. By the way, you are going to have a similar shape. You have a point here, k equals to 0, you are here, k equals to infinity, you are here. The only way that you go from here to there is a circle like this. You can put the arrows. And you can use the last two rules to determine for what value of gain k you cross the imaginary axis. For this, you need to find the closed-loop systems denominator, insert j omega and solve it. And for this example, last one, root locus exists between here and there and here and there. You can give some numbers, -4, -2, 2, 2. Let's calculate sigma of A, which is -4, -2, +2, -2. Well, this is -2, minus. Let me quickly correct this. -2 divided by m is 1 and is 3, 2. So you have 4, 2, you have -1. So basically they will intersect at this one. So one go up, one go down like this. So you can generate different root locus by applying the rules. Make sure it is symmetric with respect to the real axis. Determine where they approach to the zeros or the asymptotes, and pretty much we are applying the same rules over and over. Now I would like to talk about generalized root locus. What if you don't have the KGC on the forward loop transfer function? Well, you may have two cases. The very first case, let's say you don't want to sketch root locus with respect to a gain, but with respect to another variable. Let's say you want to sketch root locus for A. Well, in this case, you have to find the closed-loop system. And for this block diagram, this is your closed-loop system. Now you need to arrange the denominator in a particular way. Group the terms that doesn't depend on the parameter that you are interested to sketch the root locus, in this case A, and the other one that depends on A. And then divide both the numerator and the denominator by this guy that doesn't depend on A, like this. If you look at this particular form, your denominator is now in 1 plus k g of s form. Remember, we were using g or k multiplied by g to sketch the root locus. We are going to do the same. This is your new kgc to sketch the root locus as a function of a. Writing it like this, putting its pole here and here, putting its 0, which is at 0. Now we can sketch the root locus. Basic root locus starting from here exists between here and there. And there must be a point you can calculate. This is called the break-in point. I am not going to calculate right now. Root locus moves from here to there. A equals to infinity, you approach to 0. A equals to infinity, you are there. The asymptote, you have one asymptote angled at 180 degrees. And minus m is 1. A equals to 0, A equals to 0. Here is the generalized root locus for a different unity feedback structure that k doesn't multiply by g, but you are sketching root locus with respect to A. Generalized root locus second case can be any block diagram. Let's consider this interesting block diagram. First of all, for any generalized root locus that doesn't look like, that doesn't have unity feedback and kg of s on the forward loop, you have to find the closed loop system transfer function. So for this block diagram, your closed loop system between y and r can be represented like this. If you want me to post more videos about, block diagrams, how to find closed loop system transfer functions, let me know. This is not the scope of this video. For this example, let's say I am using this 1 over sk, s plus 1, s plus 2. And I would like to sketch the root locus for gain k that is appearing in an interesting location like this. It doesn't matter. Take all these, put it here. Simplify, you end up having this closed loop system. Again, the denominator matters. We would like to group the terms that doesn't depend on k and does depend on k, divide numerator and denominator by this term that doesn't depend on k, like this, you arrive having this form. Once again, you have 1 plus k g of s formula. This was the formula we derived all these rules, right? So I am going to use this formula, more specifically this, and sketch the root locus with respect to this in a classical way. If you take its poles, one of them is located here, other one is located here. Zeros, one of them is located at 0, one of them is located at -1 and 0. So in this case, starting from here, root locus exists between here and there, and here and there. K equals to 0, we are here. K equals to infinity, we are here. 0, k equals to infinity. Put the arrows. This, in this case, you know, m is 2, n is 2, meaning that root locus goes from zeros to poles. You have 2 branches, meaning that your closed-loop system will have 2 poles, and there are no asymptotes since n equals to m. And in this case, pole goes from 0 to pole, pole to 0, and that's it. Basically, this is your root locus. If you want me to do more root locus examples, or if any part of this video is not clear, let me know. We can then go from there. I can provide more explanations as necessary. All right, thanks.